Hello everyone, welcome to my channel. So this is my first video, and in this video I'm going to discuss few questions from various papers like GATE, CSIR, NET, etc. These are all going to be related to coordination chemistry involving CFSE. Now I have written down few steps which are to be followed when problems involving CFSE arise. So these are the steps. The first step is to determine the geometry of the given complex. Geometry in the sense I mean we should find out whether the complex is octahedral or tetrahedral, etc. So that's the first point, and it's very important. The second point is to determine the oxidation state of the metal atom or ion. We know that complexes are formed by transition elements, and they have a natural tendency to show various oxidation states. So it's important that we find out the oxidation state shown by a metal atom in a particular complex. Thus, the second point is also equally important like the first one. Now moving on to the third step. The third step is to determine the type of complex, which is based on the nature of the ligand. So this is also a really important step, but you should keep in mind two different types of complexes that are possibly formed. The one or the number one complex that's formed is high spin complex. High spin complex is formed when the central metal atom combines with a weak field ligand. When this type of a complex is formed, we see that the filling up of electrons will follow Hund's rule of multiplicity. So this is a point that you should remember. The next possible complex that's formed is a low spin complex. This is formed when the central metal atom or ion combines with a strong field ligand. So the point to be noted here is when this complex is formed, the filling up of electrons will not follow Hund's rule of multiplicity. So it's really important that you keep these 2 points in mind for future application. So what is a weak field ligand and a strong field ligand? This can be better understood by looking at the spectrochemical series. Now the spectrochemical series is an arrangement of ligands based on their ability to increase the delta value or CFSE value. Now I have arranged the ligands based on their ability to increase delta naught or delta T in the case of tetrahedral complexes. So these are the weak ligands. We are starting with the weak ligands. We move on to the neutral ligands, and then we move on to the strong ligands. So this is the spectrochemical series. So please make a note of this. Now let's quickly move on to the first problem. The first problem is the CFSE on the units of delta naught for this particular complex is. So the first point is already over because the first step is already over because the question already carries a hint that the complex is octahedral, which is represented or indicated by this particular hint, which is delta naught or delta O, which means that this complex is octahedral in nature. So the first step is already over, but this may not be possible or this may not happen in many cases. Some questions may not have this indication. In that case, you have to look at the number of coordination bonds formed by the metal atom. In this case, it's cobalt. It's forming 3 bonds with fluorine and 3 with water. So total of 6. The coordination number is 6, for which only octahedral is possible. So the first step is over. Second step is to find the oxidation state. Now for time being, I'm considering the oxidation state of cobalt to be X. So this is a simple mathematical calculation which you can adopt to find the oxidation state. So we have 3 fluorines and 3 water or aqua ligands. So I'm going to take 3 into -1 for fluorine and 0 for water, equating it to 0 because this is a neutral complex which doesn't have any charge outside the bracket. So equal to 0. Now when I evaluate this or when I simplify this, I get x minus 3 is equal to 0 or x is equal to plus 3. So finally, Plus 3 is the oxidation state shown by cobalt in the given complex. So plus 3 means cobalt is losing 3 electrons. So it will lose 2 electrons from the s orbital and 1 electron from the d orbital, giving us 3d6 as the outer orbital of cobalt 3 plus in the complex. Now second step is also done. We will move on to the third step. Type of complex. So when you look at the complex, we have fluorine and water, both of which are weak field ligands. Since they are weak field ligands, only high spin complexes are possible. So when a high spin complex is formed, we know that filling up of electrons will follow Hund's rule of multiplicity. And it's an octahedral complex. So what will be the arrangement of electrons? We will have T2G orbitals, 3 T2G orbitals, which is of lower energy. And of higher energy will be EG orbitals of higher energy, and we have 2 orbitals. Now I'm going to fill up the electrons. We have 6 electrons as a whole. I'm going to start with the lower orbital or lower energy orbital. 1, 2, 3, 4, 5 and 6. So we see that pairing up did not happen unless or until the orbitals were singly occupied. And I paired up the 6th electron only because all of these 5 orbitals were already filled. So I paired up. Now we have one pair and we have 4 singly occupied orbitals or unpaired electrons. Now how am I going to represent this? T2G4 Eg2, because 4 electrons in T2G orbital and 2 electrons in Eg orbital. Now this is a very important step that you should highlight in the exam. Now let's move on to the final step where we are going to find the CFSE, crystal field splitting energy. So we have a formula for crystal field splitting energy. This is the formula. The formula for tetrahedral complex and octahedral complex is the same. Only difference is the representations of M and N will vary and the constant delta T and delta naught will vary. So we are not going to think about the tetrahedral complex now. Let's go on to the octahedral complex. For an octahedral complex, M is represented, or M represents number of electrons in T2G orbital and N represents number of electrons in EG orbital. So what this minus 0.4 and plus 0.6 represents, or what is the meaning, will be explained in future videos because it has to do with crystal field theory. I will be posting another video explaining crystal field theory in future. So let's move on to the problem. Now, number of electrons in T2G orbital are represented as M and EG orbital are represented as N. Now I'm going to apply this in the formula. M into minus 0.4 plus N into plus 0.6 into delta naught. Delta naught is a constant, so don't worry about it. Now I'm going to apply the values. 4 into minus 0.4 plus 2 into plus 0.6 delta naught is going to give me minus 1.6 plus 1.2, which is minus 0.4 delta naught. Don't worry about the negative sign because it's a sign convention and energy can never be a negative value. So the negative value can be neglected. So your value is going to be 0.4 delta naught. So let's look into the options. A, B, C and D. B is 0.4. So your answer, the correct answer is going to be 0.4, which we have arrived ultimately. I hope all of you understood the first problem. Let's move on to the second problem. So this is your second problem. The second problem is, this is a pretty tricky question. So let's pay keen attention to this. The CFSE will be highest for, they've given us 4 complexes. Now what we should find out is, out of the 4 complexes, which complex has the highest CFSE value or highest crystal field splitting energy is what we should find out. Now, the options have complexes that involves cobalt and manganese. So I've written cobalt and manganese along with their outer electronic configuration. Now let's deal with the complexes separately. First complex, A, cobalt F6 3 minus. What is the first step? The first step is to find the geometry. The geometry is going to be octahedral because 6 bonds are formed. So I'm writing octahedral or delta knot. Now, the second one is to find the oxidation state. The oxidation state is going to be plus 3. I'm not explaining the calculation of oxidation state again because I've already explained it. When you work it out, you will definitely understand. So the oxidation state will be plus 3. So it's same like the previous problem. When it's plus 3, you have 3d6 as the outermost orbital. And the filling up of electrons will be T2G4 and Eg2. Because here again, according to third step, fluorine is also a weak field ligand. So a high spin complex is formed and it's going to be T2G4 and Eg2. Now the whole thing is over. I'm going to calculate the CFSE. Now for CFSE, we know it's an octahedral complex. So it's the same as the previous question. So I'm just going to write 0.4 or minus 0.4. Now let's move on to the second option, B. Cobalt CNS 4 times 2 minus. In this complex, the first thing that you notice is the coordination number is 4. So it's going to form a tetrahedral complex. And tetrahedral complexes have a CFSE which is lower than delta naught or the CFSE value of octahedral complexes according to this formula. Delta T is equal to 4 by 9 times delta naught. So delta T is going to be having a very less or a comparatively less CFSE value than delta naught or an octahedral complex. So I am just going to neglect this option because a tetrahedral complex cannot have a highest or high CFSE value. So moving on to option C, we have manganese, and from the complex it's clear that it forms 6 bonds. So it's an octahedral complex. And water, the value of water is 0. So the oxidation state of manganese is going to be plus 2. So I'm writing plus 2, which means it's losing the 2 electrons from the s orbital and retains the 5 electrons in the d orbital. Now, water is a weak field ligand, which I'm writing here. Now, since it's a weak field ligand, it can only form a high spin complex. When it forms a high spin complex, the filling up will be of this order. So 3 orbitals will have 3 electrons, 2 orbitals will have 2 electrons. Now let's quickly calculate the CFSE value. CFSE is going to be 3 into minus 0.4 plus 2 into plus 0.6. When I do this, I get minus 1.2 plus 1.2, which is equal to 0. So this also can't be the answer. Now the last option, option D, which is CONH3 6 times 3 plus. Again, it's an octahedral complex. And the value of ammonia is also 0. So cobalt will exhibit plus 3 oxidation state. It's the same after this. But the only thing that you should notice is, I'm writing 3d6 because it's losing 3 electrons, so 3d6. The only difference here is ammonia is a strong field ligand. Strong field ligand. Since it's a strong field ligand, it is going to form a low spin complex. What does it mean by it's forming a low spin complex is that the electrons are going to be concentrated in the lower energy orbitals, or the filling up will not follow Hund's rule of multiplicity. How will it be? It will be T2G6. That is, all the 6 electrons will remain in the low energy orbital, making it very stable, and the splitting energy will be higher, or CFSE will be very high for a low spin complex, because all the electrons are in the lower energy orbital. They don't go up to the EG orbital, which is at higher energy. So EG will be 0. So the splitting will be really high. So the CFSE value of a low spin complex when compared to a high spin complex will be high. So out of option A being a high spin complex, we have only two options left because we are ruling out C and B. We have only A and D. But A is a high spin complex, but D is a low spin complex. So D will only have a very high CFSE value. So option D, cobalt combining with ammonia, is the correct answer. Option D is the correct answer. So I hope you understood this problem as well. Let's move on to the final problem. We are moving on to the third problem. So the third problem is the CFSE for the following D3 metal ions. We have 3 ions: vanadium 2 plus, chromium 3 plus, molybdenum 3 plus, decreases in the following order. They've given us 4 different orders. So these type of questions are usually asked in GATE exams and other competitive exams. So it's a very important question basically. Now they've already mentioned that it is a D3 metal ion. So we have only 3 electrons present. Now I have a set of points which are to be remembered when these type of questions are asked. So I have just written down the way in which all of these elements are positioned in the periodic table. In the 3D series, we have vanadium and chromium, and in the 4D series, we have molybdenum. Now, the first and the most important point is, this is a periodic trend which most of the times we fail to understand, which is to be applied in this question. I'm explaining this now. So the periodic trend here is, when you move down the group, the value of the CFSE or delta increases. Why? Because when you compare 3D and 4D orbitals, the electrons in 4D orbitals are more diffused in space than the 3D orbitals. Hence, there is more interaction, leading to an increase in the delta value. It's a very important point that you should keep in mind. The next point is also an important point, which involves oxidation state. Here, when the oxidation state of a central metal atom or ion is more, it indicates an increase in splitting, as the nucleus with high charge or energy interacts more, leading to an increase in delta value. This is a general statement which says that when the charge of a nucleus is more, it has more interaction with the electrons. So obviously the splitting will be more and delta value will be more. So these points are the ones that I'm going to apply in the question. Now I am going to compare the ions given. We have vanadium 2 plus and chromium 3 plus. First thing that I notice here is oxidation state of chromium is more. So obviously its splitting is going to be more when compared to vanadium. So directly I'm writing chromium 3 plus will have higher CFSE than vanadium 2 plus. So this will be my first comparison, which is over. Second comparison is between chromium 3 plus and molybdenum 3 plus. They both have the same oxidation state, so I cannot apply the second point here. Instead, I can apply the first point. According to the first point, molybdenum is in 4D series, but chromium is in 3D series. So what happens? 4D is more diffuse than 3D. So molybdenum 3 plus will have more CFSE when compared to chromium 3 plus. Now I'm going to arrange these two. So the least or the most value, or the One that has more CFSE is molybdenum 3+, after which comes chromium 3+. And the least value of CFSE is seen in the case of vanadium 2+. So let's look at the options and we see that option C is the correct answer. So I'm done with all the 3 problems for today. I hope all of you understood the concepts. Please feel free to suggest some topics in chemistry which you would like me to explain in the future videos. I will definitely consider your suggestions and make videos on them. So thank you again for watching my video. Please like and share my video. And also don't forget to subscribe to my channel and press the bell icon for latest updates. Thank you.